Ja, tak. Okay, so the next part here is maximum likelihood. How many of you have done maximum likelihood estimation before? Just a few. That was also what I kind of expected. I did actually not include one thing here that might be useful. So, remembering from last week, if you have a linear model from this week, you have that the mean value is x times theta, and the covariance matrix is sigma squared times uppercase sigma. That's the distribution of y if we assume that the residuals are normally distributed. And that's the typical assumption that we'll make. Of course, it's not always true. And then we just call it a least squares algorithm. So the least square algorithm does not consider any distributional assumptions. But if you want to do tests and things like that, you need to make some assumption about what is the behavior of the epsilons. So that's one way of defining it. That's the typical assumption for linear regression, at least in the introductory courses, until you do what is called generalized linear model. That's one thing to just recognize. I've been speaking about the general linear model, but there's also what's called the generalized linear model. That's where their error structure is not normal, but say Poisson distributions, binomial distributions, whatnot, from the so-called exponential family. That's a different course. 0, 24, 24. So, again, we'll assume that sigma is known. And, well, it's called maximum likelihood. So how do we define the likelihood of some observations giving some distribution here? Yes?
Just the Gaussian assumption.
Yes?
You just take the example we had before. How good or bad would it be in that case? Like, would it work with the sun panel thing?
Yeah. It wouldn't be too bad. Because, well, it would be bad if you did it without scaling the variance and things. But when you take the correct scaling of the variance, it's reasonably okay. What I do not know why I looked the way I looked in my face was because it could be such that it's bounded to not be negative values. So you cannot have negative observations of the radiation, of direct radiation in this case. So there is a truncation there, and I don't know if that is large enough to make an impact or not. So that is probably, if you kind of disregard any observations below a particular angle, then it will probably be fine. But you have a truncation of the lower end, which will invalidate the assumption, I think.
When you said proper scaling, is it just scale to 1?
When I say what?
Proper scaling of the variance.
Yeah, proper scaling. No, that meant for the 1 over the sine of the two heights. For this particular case. Now, what I wanted to get to is, what did we do last time when we defined the multivariate normal distribution? We defined the density. I don't know if you recall it. It's 1 divided by the square root of, and then I'll write it a little bit different than last week, 2 pi, and then I have the sigma square in here to the n power multiplied by the determinant of uppercase sigma. So that's the pre-multiplier. And then you have exponential of, you can say, the usual thing that's in here. It's minus 1 divided by 2 sigma square. And then the inner product that is weighted, y minus x theta transpose uppercase sigma inverse y minus x theta. So that is the density for the multivariate normal distribution. The density is also what is the likelihood of observing a given y given when the x's and thetas are given. So that's the likelihood function. That's basically just the density in this case. And that's the only structure that we use in this course for the likelihood. So likelihood equals density in this course. You can make more complicated cases. So when you want to maximize the likelihood, what do you want to do? I want to find the parameters that maximizes the likelihood. I want to find the value of theta that maximizes the likelihood. How do you do that? Had the answer previously, you can repeat it. I take the first order differentiate of this and equal to 0. Now, before making life difficult with a complex equation here, first have a look at where does theta go? Well, it's only here and there. So we have to maximize this. So that means we have a minus in here for the exponential of minus something. It's a monotone function of this. So we want to minimize. So maximizing the density equals to minimizing what is in here because of the minus sign there. So we want to find the arc mean, arc max of theta for f of y, and it's the same as arc mean theta for what is in there. Let me write it like this: y minus x theta transpose sigma uppercase sigma inverse y minus x theta. And it's obvious that this minimization problem is the exact same thing that we solved up there. So of course the solution is the same. So the maximum likelihood estimator is the same as the weighted least squares estimator. The estimator for sigma square is a little bit different because it says n, 1 over n here. That's just due to the fact that if you take the same expression over here and differentiate with respect to sigma square and do the same thing, differentiate with respect to sigma square equal to 0 and solve, then you get to this expression here. And it does not divide by n minus p. So there's a small bias here in this estimator. Typically, you'll just divide by n minus p, but when n is sufficiently large relative to p, the difference is marginal. But it's just one thing to keep in mind that for the maximum likelihood estimator, the estimator of the variance of sigma square is biased. But the estimator of the theta value is again unbiased. I just have to check one thing. So, and we have the variance here is the same estimator of the variance of theta. So we're quite good here. Now, in real life, you don't know the correlation structure. You can specify, as for the sun example there, you can specify a function that you assume, but even that, we did not know rho. We did not know what is the correlation in time. We specified the dependence on the angle, and that was known, but not the rho. So what you do, at least one way to do it, is to make a small algorithm where you start by fixing uppercase sigma at something, and an easy thing to initialize with is just to take the identity matrix. Then you estimate the parameters of that model for the given here, solve the nominal equation, you get the usual estimate over there. Then you look at the residuals from that model and look at the variance or covariance structure of that. And then you try to say, well, can I, given some assumption about the correlation structure, what is a good value for the next uppercase sigma? And then you go back and estimate using this updated sigma, and you continue estimating that, look at the residuals, at some point it will converge. My personal experience with this algorithm is that 2 iterations and you're actually quite close. Then you're down to decimal places, that doesn't matter. If it is a simple structure. Of course, you can construct cases where it does not work as smooth. But I mean, for the cases that I've used for real data, it actually converges very fast. So I'm satisfied. This I also mentioned last week. If you want to do predictions, and what you want to do is you want to minimize the squared prediction error, then you want to look at the conditional expectation of y given x. That is the optimal predictor. That's the one thing to keep in mind. For the rest of this course, this is one thing that we'll be doing. At some point I won't say it anymore, I will just say it's the conditional expectation that we're working with because we know that it's the optimal predictor. So if you are predicting in the general linear model, we'll start with a simple case that is never happening in real life, but it's just nice to have a reference with something simple. So we want to predict the outcome at t plus L, so L times into the future. For now, you can say this into the future does not make so much difference, but we'll get to cases where it does. So we can use, in a later lecture, we'll use the same notation. So we take the expectation of this given that we know what x will be in the future. Well, that is just the conditional expectation. And the expectation of a future epsilon that's totally independent of everything else is 0. So you're left with the linear predictor part. X t plus L transpose on theta. And the variance of that, well, since that in this case we assume that we know theta, we know x, this does not give any contribution. Maybe I should just write, just so we have it for the reference, y t plus L equals x t plus L transpose on theta plus epsilon t plus L. This is the true value for the true future epsilon. There's no hat here. We look at the variance here. This is known, this is unknown. Now, in real life, we've usually estimated parameters. So the the prediction here will be the same, except that we now use the estimated value of theta hat rather than the true value of theta hat. I would say that's probably rather obvious. Now, for the variance here, of the prediction error. Now you have the same, of course you have a contribution from the future epsilon, but you also have a contribution from the theta hat not being the true theta. So what is this? Basically, the only thing that has a variance is theta hat. And if you keep in mind from over there, the variance of theta hat equals sigma square x transpose, let's take the unweighted case in this case, x transpose x inverse. That's what we have there. Now, when I then want to take the variance of x t plus L on theta hat, I don't need to have the theta in there because that is a known value with no uncertainty. And the variance of adding a constant does not contribute. So I'll just focus on this. Sometimes for easy calculation, it's interesting to have those in there, but it's just a constant, I can move it in and out. When I take the variance of a constant multiplied on something that has a variance, what do I get? Do you remember? Yes?
The constant square
I have to pre-multiply by the constant and post-multiply by the transpose. So what I have is x t plus L transpose, and then the original variance up here, the variance of theta hat, and then I transpose it on the right-hand side. That means I removed that it was transposed here, so then the transpose disappears again. So here it appears reverse of what the rule is because it's transposed already. And if I insert here, I get x transpose, x t plus L transpose, and then I have the xt x inverse, and then I have x, that should be a t plus L, and then I forgot to add the sigma square somewhere. So that's what I get as contribution from the variance of the prediction when I do not know theta, but I estimated it. And when I then add with the sigma square I got from the epsilon t plus L, I have this expression over here. So note that this x transpose x here, those are the full data matrices of all the observations that you used in the estimation of theta, and the xt plus L are just, you can say, one column vector representing the actual values that you want to make predictions for. Now, what do I want to do here? I'll skip that. So, predictions in the general linear model, what I said is that you have to specify some measure of uncertainty. And there are multiple ways of doing that. One way is to get the variance. Another way could be to give the standard error, if it's just a univariate measure. But you can also give a prediction interval or confidence interval. So one way of doing that, well, the typical way to do that is to say that if you want to make a prediction interval with some coverage, you look up the relevant quantile in the t-distribution with n minus p degrees of freedom. Now, if n is sufficiently large, you can just use the normal distribution assumption and use the, you can say, 1.92 as your factor there, or you could just use the number 2. Later on in the course, we'll just use the number 2 as an approximation of that one there. It's close enough. Because in some cases it's not, it's just an approximation. Here it's exact. So, I mean, do whatever that you want to do there, but write what you do. If I just see a factor of 2, it's not good enough. You see the normal distribution without considering n is sufficiently large. It's also a small error. If you just use the t-distribution everywhere, no questions asked. And you can say the computer is happy either way. It just has to specify the number of degrees of freedom. That's the only difference nowadays. In the old days, where you had to look up things in a table, it was different. Whenever you could use the normal distribution, you did not have to look anything up because you knew which number to use. So you take the quantile, and then, well, of course, you start with the predicted value. You take the quantile, multiply it by the standard error, and then this scaling factor here. That is, how uncertain is it? And this term here, as is the same term we have down here, that comes from the uncertainty of the parameters of theta. What is the interpretation of that? Let's just do it in a simple linear regression setting. We have some data. We fitted a straight line to this data, and we were happy. We got some estimates of the variance of this, and then if I draw this for some different values, do you know what it would look like? If I want to make an estimate, let's say in here, I should take another color. Now I kind of started it a little bit. The further you get away from the mean value of x, the further you get away from that with these values out here, the more uncertain is the estimator. Now I'll over-exaggerate a little bit. What shrinks this variance is if x transpose x is large. That means if the values that you have in x are spread out, then you get more information. Then you reduce this contribution. And the closer the point you want to make a prediction for is to the mean value, the lower the variance is. But the further away, the higher the variance is. That's just the one thing you have to keep in mind. And you can say the highlights from today, it's the usual estimator of sigma squared. Then we have the ordinary least squares estimator and the weighted least squares estimator with this definition. Maximum likelihood in this sense is the same estimator as for the weighted least squares estimator, but not the same estimator of sigma hat. And the conditional expectation is the optimal predictor. And this is how you get confidence intervals or prediction intervals. That was what I wanted to show for the slide part. I would just want to add a small R example just to give you the code that I used. See if this works. So the small example that I fitted earlier on, how to make that work. I will first define some data. And then this was what I kind of had in before. Just to plot the data. This is just trimming how the plot looks like. And I should probably make some more space over here. Then I will use what is called a matrix plot in R, which gives me plotting multiple columns at once. The rest are arguments out here just to say that I want to have both points and lines in between things. So the red ones here are my predictors. I'll add a legend. So the red ones are my set values, and my black points are my observations. And then I'll do a linear model. I could, of course, do it with matrix algebra before, but I might as well just use the built-in LM function. There's one thing to note here. That is that I used LM of z plus I of z square. If you make a formula and you do something to the second power, then you get interactions. But the interaction with yourself is reduced to just being itself. So if you actually wanted to calculate the product of z squared, then you need to say, I really want this, so I want the identity operator. I want this calculated for the particular one. And also notice that I did not add a 1 in here to get the first parameter. It's there by default. It's just some, you can say, odd choices that are made to make life easier when you do other things. And here I get the estimated parameters that we have previously on the slide. And there's also uncertainty standard errors related to those and p-values, but we'll get back to that at a later point in time. But this is the usual way that you do things. And if you've done simple linear regression, the main difference here is there's just an extra line for the extra parameter. There's things about collinearity and stuff like that, but you can learn about that in the multivariate statistics course. To do the plot from the linear model object, I can get the residuals from that. I can get the fitted values out. So now my data contains 2 extra columns, one with residuals and one with the fitted values. And now I'll just make similar plots. These are the observations and a line indicating the fitted values. And then I'll show the residuals as well. The plots in the slides were made using what's called ggplot, which is doing some fancy things. It's a bit more complicated to actually construct the plots. So I will tend to just use the standard plotting facilities, not to make things overly complicated. I'll share this code, but the code for making the plots is there if you want to see it. But if you don't care, just disregard the bottom part. So that was one thing, just to give you a little bit of code that can also help you out a little bit in the exercises, but you could, of course, also write it as linear algebra notation. If you want to do that in R, there's one thing you should keep in mind. If you want to do a matrix product, a few things you should keep in mind. So what is important to know? In order to estimate theta up there, first of all, I need to construct my X matrix. For the model, I need, I wiped that out. I column bind first a column of 1s to get the intercept. Then I want to have set, which is data $set. And then I want to have set squared. Oops. Like this. So now I have the same matrix as in the slides. So what I need to calculate to get theta hat is I need to first find X transpose X inverse. So I take the transpose of X like this. And matrix multiplication is percent multiply percent x. That's one of the odd things here. By default, R does element-wise operations. So if you want to do it matrix vector-wise, you really want to stress that. To invert something, you solve it like this. And then I need to multiply with x transpose on y. So then I matrix multiply with the transpose of x, and I matrix multiply on data $y. That gives me the same estimate as before. So this is the manual way of doing it. But I'll share that code as well, so you have it, because it could be useful for the exercises. Actually, I will say that you could do it by hand. It's just not a lot of numbers, but I recommend that you actually just get R or MATLAB, whatever, up and running, and just do the calculations there. Then the exercises are fairly easy. There's one more thing that I would want to just talk about. Some of you ask me, when are the assignments? Come on. So what I did was to go into the calendar and write when are the different assignments, the 4 assignments, when are they opening, and then in that also writing when is the due date. But let me just find the first one, which opens next Friday. Something is a little bit slow right now. So it should say down here, assignment 1 becomes available, and the deadline is September 29th. So you will have, for the first 2 assignments, you have 2 weeks to complete them. And I looked a little bit, should I move a little bit around on these deadlines? I'm somewhat flexible, but we should all agree on when they are. So now I have made a set of deadlines. So you have 2 weeks for the first one, and then you have, and the way I've done it is that on Thursday night is the deadline for handing in, and then you get the next one on Friday morning. Just so that it's like one is out before the next one is available. That thing I will not change. So the second one has deadline the day before the autumn break, where you get the third one. We could put the deadline for this one to be in the autumn break, if you would like that. Extra week. No, you want to have a break. That's good. I want to have a break too. But I have to work. That's life. But that's actually the one. And then for the last 2, then you get a little bit more time. Also because my experience is that the later you get in the semester, the more things that you have to kind of deal with. So there you have at least 3 weeks. The last one I've set to have deadline December 1st, which is the day before the last lecture. Sometimes people ask, can't I have that sometime in the exam period? Now I would say this time you actually have from November 11 until December 1st. I think 3 weeks should be sufficient. And then the time for the peer evaluation, I will give you, including the date that is the formal reserved date for this block here in the schedule. So at least you have that day you can use for peer evaluating. And that's close enough, but not too close to Christmas, so that if there are things that have to be resolved, there is time to look into it. And hopefully get things resolved before Christmas. those were, you can see, some of the things I had for questions from last week, or also by email over the week. Regarding getting help, I might as well just say that now. I prefer not to answer individual emails. Of course, there are cases where things are very, very unique for you. You have your own problem, and no one else has a similar problem. How likely is that? Not so likely. So what I will do is that in CampusNet, I will write a message, and then you should make a comment to that message if you have a question, and then I'll reply with an extra comment to that one. You can say it's not the perfect system, but it's an easy, accessible system. What it means for me is every time you make a comment, I get an email. So it's easy for me to know when you wrote a comment, as in a question. It's not so easy for you to see when did I reply to something. So, but when we get to it, I will try to do it within 1 or 2 days, generally. And that means that everyone gets the same answer. And I like that. So whenever if I also have a question here during exercises and whatever, where I say, well, everyone should have that answer, then I will just add that to everyone. To be fair to everyone, but also because you might be spending time on something that is actually not worth spending too much time on. Typically when you are stuck in something, you're not the only one who's stuck there. And you can say, it's not my preference to have you all sitting stuck somewhere. It doesn't make you much smarter unless you invent something that has not been invented before. But that's not the entire purpose of this course. Are there any other questions right now? It does not seem to be the case. Then I had time to do the things that I skipped, but that's how life is sometimes. Yes, and for the exercises, one thing I did not say last week either, that there are sample solutions on the book webpage, but those that are on the book webpage have some errors in them. So therefore, for chapter 2 and 3, there are, in CampusNet, I've uploaded solutions. Also for exercise 3.1, I uploaded some code, some R code that solves that one, just so you had that as an alternative solution. And for one of the exercises today, actually the solution is using a method that you will learn about next week, but the result is the same. The predicted value is the same. There is something that they're using an F operator to use what they call a local trend model. But we'll get back to that next week, just so that when you read something in a solution that doesn't make too much sense, it's not because you did not pay attention. Well, you did not pay attention to what I'm going to say next week, but that's okay. It's a causal system. Do you know what that means? For something to be causal? Anyone not knowing it? We'll get back to that in a later point in time, but I think it's good to have that line of thought already now. What does it mean for a system to be causal?
It means that one thing causes another. I think I have some idea, but I don't think I can put it into words.
Anyone who can say, what is a causal system? Yes?
A system that only depends on past values.
Past and current. Yes, so it's a system that does not depend on future input. That's how I prefer to phrase it, but it's the same. That is a causal system. And most systems are causal. Sometimes, if you want to make a perfect system, it should be non-causal. How many have tried a noise-canceling headphone? Are they good? They help at least. If you could predict the noise that is coming in a moment, if you knew it exactly, it will be perfect silence in there. But now they have to estimate, have to measure the sound, do the calculations, what should I do to compensate, and then play that sound on top of what you're hearing. So you'll always be a little bit behind. But if you knew what was going to happen, you had a non-causal system, and you can make perfect noise cancellation. Keep that. I think that's one of the easiest things to kind of, where you can see what it means. Okay, but go ahead with the 2 assignments today.